Hello everyone. So today we'll start week 8 of our tutorial session, and this will be the last week, I guess. Let's start. So we'll be, as usual, we'll be solving all the previous year, some of the previous year problems and assignment problems, so that you can solve the current year assignment problems on your own. So let's start. Okay, so first question is, the upper edge of a thin homogeneous plate is parabolic. So we have a thin homogeneous plate like this. This is the plate, and the upper edge is parabolic. So the parabolic edge plate is there with a vertical slope at the origin is O. So at the origin the slope is vertical like this. See figure, and the plate has thickness T. So this thickness is T. Okay, and length is B. So this length is B, and height is H. This height is H, and mass is M. So total mass is M. The mass density rho, the plate is constant. So mass density is constant means mass per unit volume is constant. For any given volume here, you will have a constant mass. Okay, and its moment of inertia about x-axis. So it's asked that its moment of inertia about x-axis. What is the moment of inertia? So how do you start doing the problem? So moment of inertia about x-axis, we know from definition. We have already discussed this in previous classes, that moment of inertia about x-axis will be y square dm. Okay, now we can write this dm, the mass of a unit volume, as rho dv. Okay, rho is the mass density, that means mass per unit volume, which is given constant. So this becomes rho integral y square dv. Okay, now if you look at this small mass element, you see this is a long, it's like rectangular prism, or what is it called, a parallelepiped. It's a cube, but long elongated cube kind of structure. So how can we write this dv? How can we express this dv? So you see, along this direction, along z direction, this thickness does not change, it is homogeneously thick. But along x and y direction, the length are not uniform. So because along z direction it is uniform, we can write this dv equals this thickness times some small element along x direction and some small element along y direction. So t dx dy. So what we have got, rho integral y square rho t dx dy. Okay, now we have to calculate this. Fine. Now when I will be doing this integral, look, this y and x, now everything has become in one plane. One plane means, so we can ignore this z plane, because z plane's contribution only this thickness t. So we have already taken care of it. So if the whole problem becomes a 2D problem, where we have x direction and a y direction, and this is our parabola. Okay, and we have to calculate this integration y square dx dy. fine. It's not exactly okay, so let me, it's fine. Yeah, so y square dx dy. Now if you consider, so what does this integral means? It means the second moment of area under this curve. So I'll explain what does that mean. So along x direction, you see this length is b, and along y direction this length is h. So let's say this, here we put our cutoff like this. So this direction is b and this direction is h. So this point is 0 0, this point is b 0, and this point is b comma h. Okay, now we have to do the integral, but because it is a parabolic shape, it's bounded by a parabolic shape, this y and x are not independent of each other, so we have to take care of that while integrating. We can't just write it like y square dy times dx. We cannot write it like this. We cannot write it like this because x or y are not independent of each other. So we will be doing one of the integral first, then the next integral second. So let's do the y integral first. So let's calculate ix equals rho t integral dx y square dy. So this will give some x dependence. This will give some x dependence. So till what point? So okay, so dx is like, now let me draw the dx and dy here. So this is dx and some other along y direction. So this is dy. Sorry. So this is dy and this is our dx, or here if you write this is dx. Okay, so this dx and dy. So what if we do y integral first from some 0? So y goes, so y starts at 0, so we have to do the integral over this plate, right? So we'll start at this y goes from 0 to some value of y at x, right? For any given point, y will start at 0 to and go from some value of y at x, right? So the integration limit will be y x. Okay, so let's calculate this integral. Rho t integral dx, this is y cube by 3. Let's write it this way, which equals rho t integral dx y at x cube by 3. So y as function of x, so rho t by 3 integral y cube dx. This is what we got. Now we ask, how does y depend on x? What that means, what is y as a function of x? That we will be calculating from this parabola. So let's copy this, yes, and paste this here. Yes, now let's copy and paste this here. Okay, so if you look at it, so this is a equation of parabola. What kind of parabola? So you can write this y equals root x, right? So x So for every x, this y line goes as root x, or we can write is y equal x equals y square with some constant, right? So you can take constant here also, and you can convert this constant to another constant, gives ky square. Now what is this k? So for this k, we know some stuff. One is at x equal to 0, y should be equal to 0. So if you put x equal to 0 here, x equal to 0 here, y you get y equals 0 here also. But at x equal to b, you should get y equals h. So let's put that value. So at x equals b, y equals h. So b equals k h square. So this implies k equals b by h square. So the equation of this parabola becomes x equals b by h square times y square. This is the equation of the given parabola. Fine. Now look, we have to find out what y cube is. Okay, so let's find out what y cube is. So from here we can write y square equals h square by b x, right? Which implies y equals h by b to the power half x to the power half, which implies y cube to be, sorry, this is h, so h cube by b to the power 3 by 2 x to the power 3 by 2, no sorry, x square we had, no, yes, b to the power 3 by 2 x to the power 3 by 2 h cube. Now let's go back to our integral. So ix was rho t by 3 integral y cube dx. So what have we found? Y cube to be, from here, so let's write it down, rho t by 3, y cube is h cube by b to the power 3 by 2 x to the power 3 by 2 dx. Okay, now let's put the limit on x. Limit x starts from here and goes to till b. Okay, so this is 0 to b, and rho t by 3 h cube by b to the power 3 by 2, and you get x to the power 5 by 2 by 5 by 2, 0 to b, so 2 by 5. Let's get a new page. So here you get rho t by 3 h cube by b to the power 3 by 2, 2 by 5 b to the power 5 by 2 minus 0. So you get 2 by 15 rho t h cube b to the power 5 by 2 minus 3 by 2 which is just b. So 2 by 15 rho t h cube b ix. So this is our final answer. And let's go back to the question. So 2 by 15 rho t h cube b. So this is our answer. Okay, so you have to do this. So the trickiest part is to do this integral like this. Now one thing I would like to mention, that you could have done the x integral at first also, but you have to keep in mind one very important thing. I'll just point it out and you try it yourself. Now let's say what was the integral we had in our hand, which was y square dx dy, right? I am not writing the other part. So if you want to do x integral first, so you keep y square dy the way we kept dx aside, dx, so the way we kept dx aside, and did the y integral. Similarly, we keep y integral aside and do the integration on x. But there is a catch. Catch is, for y integral the limit went to 0 to some y as a function of x, but for x integral the limit is not from 0. Let's say you are here, you will go like this, right? But so the limit is not from 0 to b. Don't put the limit 0 to b blindly. If you put 0 to b blindly and do the calculation, you get this answer, which is wrong. Very important. You have to put the limit from some x as a function of y, some x as a function of y to b. Okay, some x as a function of y to b. So what you will get, you will get y square, you will get integral y square dy, and b minus x as a function of y. So you will get y square by square dy minus y square times x as a function of y dy. Here you can put this limit from 0 to h. Then you will get this 2 by 15 and rest of the part. Otherwise you will get 1 by 5 or something. Be careful about this kind of integrals. Always remember, always draw these lines, these elements, and see in which direction you are doing the integration first, and that's how you choose your limit. Because in y direction we had, this is our plate, you have to cover the plate. If you so for this plate we had y goes from 0 to b and x goes from some y to b. So y goes from 0 to h and x goes from some y to b. This is very important. If you do x goes from 0 to b, you basically integrating like this whole area, something like that, or probably you will be getting the area of this part, not the other way around. Okay, yes, fine. So that was question number 1. Very interesting problem, tricky, little bit tricky problem. Okay, next question, determine the product of inertia. Okay, remember this is not moment of inertia. They are asked the product of inertia, which is the off diagonal term of the moment of inertia tensor. So it is off diagonal term of the moment of inertia tensor, Ixy. So moment of inertia tensor you can write is as I equals Ixx, Ixy, Iyx, Iyy. So these are principal moment of inertia and these are product of inertia. The other two, these are moment of inertia and these are product of inertia. So Ixy you have to find of the right triangle in the coordinate system. So this is the right triangle and this is the kind of coordinate system you are given. Assume surface mass density sigma equals 1. So it's a 2D problem and we have to find out the product of inertia. So Ixy is basically moment of product xy and dA. Oh sorry, mass dm. Okay, now if you have surface mass density sigma, then we can write dm as sigma dA. So sigma is surface mass density. Now sigma is constant, so sigma xy dA. The same problem, the same approach is same, but the problem is a little bit different. So dA is basically like this, so you would have dx and dy. So sigma xy dx dy. Okay, now same way we will be solving that problem, this problem with, let's say, you can keep any one fixed and do the other the way we did before. So let's say we fix x first and y dy, we do the integral. Now when we choose to integrate along all the y axis, so we have starting from 0 to this line, right? Sorry, in the x axis. So in y axis this is 0 and to some to this line. So this line is basically y as a function of x. Okay, so it will be 0 to y as a function of x. So what you get is x dx. This is y square by 2, 0 to y as a function of x. So sigma x dx by 2 y square as a function of x. Now we have to find out what y square as a function of x is. How do we find it out? From the equation of this line. So we all know that equation of a line with this slope in intercept representation, it is called this is b and h. So b and h. So this intercept representation, this is x direction, can be written as x by b plus y by h equals 1. So this equation represents this line. Okay, so x by b plus y by h. So from here we need y. So y by h equals 1 minus x by b. Y equals h minus h by b times x, or h into 1 minus b. Okay, so let's write h into 1 minus x by b. Okay, now let's put it here. So we had I xy to be this. Okay, this. Now let's put y square. So y square is h square times 1 minus x by b square. So this becomes h square minus b minus x whole square by b square. So it is basically h square by b square, yes, times b minus x whole square. So I xy becomes sigma by 2 integral x times y square, which is this h square by b square, b minus x whole square, times this is another x, it is already written, and dx. So let's take h square by b square out, x times b minus x whole square dx. Now x limit is 0 to b. Okay, so sigma h square by 2b square, this is h, 0 to b. So this is b square minus 2bx plus x square dx. And so let's assume this is there. So 0 to b square x minus 2bx square plus x cube dx, right? And we get b square x square by 2 minus 2b x cube by 3 plus x to the power 4 by 4, 0 to b. And we get b to the power 4 by 2 minus 2 by 3 b to the power 4 plus 1 by 4 b to the power 4. So what do we get? So b to the power 4 we take out 12, 6 minus 4 plus 3, which is 8. Hold on a minute. 8. Okay, so 9 minus 8 is 1 by 12. So b to the power 4 by 12. So this part times this, so Ixy becomes sigma h square by b square times, that is a half, times b to the power 4 by 12. So this becomes, implies Ixy becomes sigma 1 by 24 sigma h square b square. So this is what we get as our answer. Let's check if it is 1 by 24 b square h square. Yes, so this is our answer, and the sigma is given to be 1. That's why the sigma is not in the answer. Fine. Okay, so let's continue. Next question: consider square of mass m shown in the figure. The length of each side is a. So there is a square, and length of each side is a, like this. All of these sides are a. Assume the mass density sigma is uniform. So the mass density here sigma is uniform. Consider the coordinate system in the shown in the figure. So this x-axis and this is y-axis, and the origin with the origin at the corner z out, and this is the origin, and there is a z-axis, let's say like this, something perpendicular to the plane. Will the three principal moment of inertia for the given square about the given origin be equal? Question is, will they be equal or not? So all the options have to choose from these options. So all three principal moment of inertia are equal by symmetries in the square is symmetric object. Two principal moments of inertia about the principal axis in the plate of the square are equal, but one about z axis will be different. All three principal moments of inertia will be different since the mass distribution is not symmetric about the given origin, cannot be determined from the given. So all three moments of inertia, so this for sure the moment of inertia about z axis would not be same, because there is no mass in the z axis, only on that plane, and if you think of rotation, it would not be the same. So this is wrong, this is wrong. Now two principal moments of inertia over principal axis plane of the square are equal, but on the all three principal moments difference is the mass distribution is symmetric about the given origin. This is the right answer, because the mass distribution about this origin is not same. If the mass distribution is not same, then the moment of inertia will not be equal. If the origin was like this, then it would have been same. Okay, so next question is a rectangular prism of mass m, sides a equals 3c, b equals 2c, and c. So there are three sides. A equals this a, this is b, this is c. So like this. So along x-axis it is a, along y-axis it is b, and along z-axis it is c. Okay. Yes. So the mass of the prism is 10 gram. So mass is 10 gram. What should be the value of c, so that the largest principal moment of inertia, largest principal moment of inertia is this. So I wouldn't be deriving the formula for moment of inertia, but for this kind of setup, but write it down. So for three principal moments of inertia is 1 by 12 for this cubic setup. M for x-axis is b square plus c square. The other two, okay, Iyy will be equals 1 by 12 m c z and z and a, and izz equals m a square plus b square. Now this convert this, a equals 3c, b equals 2c. So b equals 2c, it becomes 1 by 12 b square by so 4c square plus c square. So 1 by 12 m 5c square. So this becomes 1 by 12 m c square plus a is 3c, so 9c square. So this is, we write it as 5 by 12 mc square, 5 by 12 mc square, and this is 10 by 12 mc square, and here we get a is 3c, which is basically 9c square plus 4c square, so 13 by 12 mc square, which is the largest, this one. So largest is 13 by 12 mc square. This is 1000 gram centimeter square, and m is 10 grams. So 13 by 12 times 10 c square equals 1000 gram cm square. So grams, so c square becomes 12 times 1000 by 13 times 10 cm square. So c becomes root over that, and it would approximately comes around 9 point something centimeter. So none of the above matches. We'll just choose maybe 11, the closest one. Okay. Oops. Here. Okay. So that was question 4. Now next is also very easy question. So it says that 4 equal point masses. So you have point mass here, 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 and here. 4 equal point masses is located at the 4 corners of a square. So you can imagine a square like this. Okay. So this is very important. So this is not very imaginable straightforwardly from this diagram, but it says that 4 corners of a square, they are attached to an axis passing through the center of the square by strings. So there is an axis and there are strings attached to it. All the masses are rotating about the axis with the same angular velocity omega. So this axis is rotating, so it's like rotating like this, and the masses here are also rotating around this because of the rotation of the axis. So they always remain in the shape of a square. So at any moment, if you see all the 4 points, you can make this kind of a square that I just drew. Okay. What is the total torque due to the tension and the force strings? Very easy question. You have to just think of in terms of what are the direction of force and what is the definition of torque. So torque is R cross F. So R is the position vector about a point, no, position vector from axis to the mass and force on the mass. So you have to think in terms of those lines. Okay, so what will be the answer then? um, so the answer will be, okay, so for every uh, mass, the position vector from the axis is along this direction, and the force, so it is the axis is rotating, and that's how we're getting a centripetal like force, which is also in this direction. So this all the r cross f will be equal to 0. So the total force will be, total torque will be 0. Okay. Okay, so we have a few questions left. Let's do this. This is a very interesting question, and it looks a bit weird, but it is not. So it said that an table is used to study the elastic motion of flexible spacecraft models. So air table. Okay, so this is called an air table. You see this dot dot hole. So pressurized air escapes from numerous small holes. So these small holes, air escapes from there in the horizontal surface. It provides a supporting air cushion for the largely eliminated friction. So this thing wants to rotate, and because there are air flows like this, it provides a cushion and which helps reducing the friction. The model consists of a cylindrical hub of radius r. So this, at the center you see this this guy is called a cylindrical hub. Okay, so this cylindrical hub of a radius r, so it has a radius r and four appendages of length l. So these are called four appendages of length l. So these guys each have four appendages of length l and small thickness. So little thickness is the figure in the, see the figure. So, and the hub and the four appendages all have the same depth d. So this length from the horizontal to the top surface all have the same depth d, and are constructed of the same material of uniform density rho. So all are considered same material with uniform density rho. Assume that the spacecraft is rigid, and the moment m which must be applied to the hub to spin the model from rest to an angular velocity omega in the time period t. So the question is asked, the moment m that must be applied to the horizontal spin model from an angular velocity omega to a time period tau is for the time period tau. So okay, so what will be the moment? Equals I alpha. Alpha is the angular acceleration, and I is the moment of inertia of the whole system. Okay, now what is alpha? Alpha will be angular velocity omega over it in a time period tau, so omega by tau. So moment becomes I omega by tau. Now what is the only unknown thing in this equation? This I. So moment of inertia of the whole system we have to calculate. Okay, so this system has several stuff. So first is, let's do it one by one. So we have a cylinder like this. Okay, so it has a radius r, and from here we have let's say rectangular or with some thickness, this guy, this and this and this. Okay, this is part of the drawing. So 5 total components are there. One cylinder, 4 rectangular blocks. So the moment of inertia, so total moment of inertia will be about this axis. This is very important. You have to define the axis. Sorry. So about this axis. Why this axis? Because the whole thing when it will rotate. This is the axis it is going to be rotating. So all the moment of inertia we'll have to calculate about this central axis. We'll have I for cylinder plus 4 times I of the blocks. So these blocks are called appendages, but I'll just call it blocks for simplicity. So I blocks. Okay. Okay. So let's calculate I cylinder. So I cylinder we all know this formulas I am not going to derive. You look at the lectures or if it is in your course. So I cylinder is half mr square. Okay. The moment of inertia of a cylinder passing through its origin, like this. Can you see? Yes, like this. It's half mr square. Simple, the good old formula. Now let's convert this mass in terms of rho times volume times r square. Okay. Now what is the volume of it? So pi r square h. So half rho pi r square, and h is basically d, the depth. See, this is the depth. This is the depth. So pi r square d times r square. So what do we got? Half rho pi r to the power 4 d. This is I cylinder. Okay. So let's solve it. Now I block. So for a rectangular block like this, if the axis passes through its middle or its center of mass, its own center of mass, the moment of inertia is 1 by 12 m L square, if the L is the length. Okay. But so that will mean that center of mass is, so this is, if it was rotating like this, then the center of mass rotating around this axis, center of mass. So how do we find out what is the moment of inertia around this axis? We apply the parallel axis theorem. We just shift it. So how much? The length m L square amount of shifting will be happening. So then m x square, let's say this cylinder like this, and so this is the x, this is x. So what is x? X is basically the whole length is L, so this much is L by 2, and there is r of the radius, so r plus L by 2. So 1 by 12 m L square plus m times r plus L by 2 whole square. Okay. Now let's kind of break it down. 1 by 12 m square plus m times r square plus rl plus L square by 4, which is basically 1 by 12 ml square plus mr square plus mrl okay, plus ml square by 4. So these two terms we can add them. So what will you get? 4 by 12, right? So 1/3 ml square plus mr square plus mrl. Now also the mass. So for this mass, so what now, let's write mass as, so now we have this block like thing, right? Okay, anyway, sorry. So we have this block like thing, so this mass will be rho v and rho times the lengths, side lengths. So what are the side lengths? Side lengths, we have L D T. So rho L D T. Okay, so M is common, so we get rho L D T 1/3 L square plus R square plus RL. Okay. Okay. So now the I total will be I cylinder plus 4 times I block. So I cylinder we got half rho pi r to the power 4 d. So half rho pi r to the power 4 d plus 4 rho L dt 1/3 L square plus R square plus RL. Okay. What can I take common? So rho we can take common, d we can take common, so rho and d, so half pi r to the power 4 plus 4 L t 1/3 L square plus R square plus RL. So I total we got. Now the moment, I times omega by tau. So moment becomes rho d omega by tau half pi r to the power 4 plus 4 L t 1/3 L square plus R square plus RL. Okay, so this is what we got as our answer. Sorry. Okay, anyway, so let's find out if it is there or not. Omega r, so this tau is, so 1/4 half pi r to the power 4 plus 4 lt plus 1/3 r L square plus RL plus R square. This is common, so omega rho d. This is what we got, omega rho d by tau. So option B is the correct answer. Okay, fine. Question number 7, we have there is a helicopter problem. The typical rescue helicopter has 4 blades. Each has 4 meter long. Each are 4 meter long. So each is 4 meter long and has a mass of 50 kg. These blades can be approximated as thin rods that are rotate about one axis. So these blades are here, and it rotates like this to the length. The helicopter has a total loaded mass of 1000 kg. Calculate the rotational kinetic energy in joules. So what is rotational kinetic energy? Half I omega square. Omega is the angular velocity and moment of inertia. Okay, so omega is given 300 rpm. So omega is 300 rotations per minute, which is equals 300 times 2 pi by 60, right? Rad per second. So that will be like 10 pi rad per second. Okay, now so moment of inertia of a single blade along this rotation is 1/3 ml square. So total I will be 4 blades times 1/3 ml square. So 4/3 ml square, which is equals 4/3 m. Mass is 50 kg, L is 4 meter, right? So 50 kg times 4 meter square. So the kinetic energy becomes I omega square. So 10 pi square. So let's calculate this. So 4 by 3 times 50 times 4 times 10 times pi square. Okay, hold on. 3.14. Okay, by 2, there is a half involved. 0.5 times. Oh, sorry, this is not 4. This is 4 square. So this is 16. So I missed something here. 16. So we get 523,845 joules. So you can write any answer between 5,0,0,0,0 to 6. This is the answer, and this is not an MCQ. This is just a normal question, just a answer type question. Okay, so this was question number 7, and the final questions is mass m travels at a speed. So there is a mass m travels at speed v0, which is perpendicular to a stick. So this is a stick and it is perpendicular to it. Mass m and length L, which is initially at rest. The mass collides completely. So the mass collides completely inelastically and stick to one end. It just sticks like this to it before and after the collision. Which of the following statements it is like this, and it just rotates like this. So momentum is conserved, but angular momentum is not conserved. Angular momentum is conserved, momentum is not conserved. Both momentum and angular momentum is conserved. So this is a closed system. Here inelastic collision is happening, so both angular momentum and angular momentum are, even without inelastic collision, for elastic collision also, so it will be conserved. So both momentum and angular momentum are conserved. Okay, that was it. Hope so. I'll just quickly recap everything. So here we are asked to calculate the moment of inertia around x-axis. So what we learned is we have to calculate this, and we have to basically do this integration. But for this integration, we need to find out the equation of this parabolic line, and this parabolic line's equation is this with some boundary condition. We found this is the equation. With help of this equation, we put it back and do this integration and choose our limits properly and get to this result. So this was the last problem. Um, that will be it for this semester, and it was great experience for me. Thank you. Bye bye.